Welcome everyone to Chapter 9 lecture. We're going to talk about electrons in the atom and a little bit more about the periodic table. I know we're skipping from Chapter 4 to Chapter 9, and then we're going to go back to Chapter 5. Our book's a little awkward in its arrangement of the chapters, so we're going to start Chapter 9. Chapter 9 will still technically be a part of Unit 3 and not Unit 2, which is what we're starting, I guess, next class. We finished Unit 1 last week, but Chapter 9 really is going to do us a lot of justice in the long term of this course. We're going to talk about orbitals, electrons, how they behave. Electronegativity is going to be a big thing that we want to discuss. And so it's just really helpful to get this chapter out of the way. I definitely recommend reviewing this chapter again once we go to Unit 3 because some of the problems in Chapter 9 will be on Unit 3, and I'll point out which problems those are. So the big things is we want to understand the atomic theories that are presented in today's class. So we talked about a couple atomic theories presented by Dalton and Rutherford and other people in, I believe, Chapter 4. In this chapter, we're going to talk about a little more concrete theories that actually have good prediction powers. And so we're going to talk about the Bohr model and quantum mechanics. We're going to mainly apply the Bohr model, which is not as powerful as quantum mechanics. We're going to identify the quantum mechanical model and then kind of put it to the side for the most part. We're going to talk about electromagnetic waves, a little bit about their mathematics, things of that nature. Orbitals, so these are where we put electrons. These are the essential mathematical constructs that house our electrons. We have a couple rules about how electrons group in these different types of orbitals. And then we're going to get into some electron configurations as well. These two are going to be mostly what your problem solving is going to be about. And so just keep that in mind as we go through. So we have various models of the atom. So I mentioned Bohr, or not Bohr, but Rutherford and Dalton. We also discussed Mendeleev's periodic law, which kind of described why things or grouped things according to their increasing atomic number and their reoccurring properties. We're going to understand a little bit more why those properties are reoccurring based on the electrons and the orbitals. Today we're mainly going to focus on the Bohr model, which came up in the early 1900s. What was great about the Bohr model is it almost perfectly approximated the hydrogen atom, which is very good for 90% of cases. However, 10% of cases, it's really going to fall apart. And as you get more and more complicated, that 10% becomes a larger and larger percent of what you're dealing with. The quantum mechanic model, which we still use to this day, only improved on the Bohr model in a simple way in that it perfectly solved the hydrogen atom. And it pretty well approximates most other circumstances. So where the Bohr model is almost perfect for the hydrogen, the quantum mechanical model does a pretty good, almost as good job for nearly every other thing out there. So big improvement, even though we went from approximating the hydrogen atom in the Bohr model to solving the hydrogen atom in the quantum mechanical model. That solving of the actual equations gave us a lot more power. You don't need to know this, but fundamentally that's the difference or what separates the Bohr model and the quantum mechanical model. So I won't make you memorize people's names, but Niels Bohr was a famous scientist. Erwin Schrödinger was a famous scientist. Bohr was responsible primarily for the Bohr model or Bohr representation of the hydrogen atom. Schrödinger and Dirac and some other people were responsible for quantum mechanics. Schrödinger is famous for the Schrödinger's equation, which solves the hydrogen atom. Albert Einstein and a whole bunch of other physicists were all involved in the quantum mechanics movement in the early 1900s. Bohr basically came out with his model, and he was perfecting it actually in the 1800s, but came out with it in the very, very early 1900s. And in the 1920s, 1930s, we really hammered down quantum mechanics at the early stages. So we're going to talk about light. So light is just electromagnetic radiation. So this is an electric wave and a magnetic wave flowing together in orthogonal directions. This just means at 90-degree angles from each other, or right degrees from each other, right angles from each other. You don't need to know this. It's just what it is. The speed of light travels at this speed. We talk about photons as being the particle part of light. So light has both wave and particle properties. When it behaves as a particle, we typically talk about that as a photon. And since white light is usually considered waves, if we take any point of this wave, that would kind of be the photon. Now, this is not a light wave. This is a physical wave through water. We sometimes use these to show wave mechanics in a more intuitive way because it's something we're used to seeing, whereas you can't see the wave mechanics of an electromagnetic wave. And so here is our kind of mathematical diagram of a wave. The most important thing in all of this diagram is you want to understand wavelength. Wavelength, period, and frequency. So period and frequency aren't on this. We have trough and crest, which are the bottom and top. The amplitude is the difference between the trough and the crest. We're not really going to be concerned with those quantities so much. The wavelength is the distance from one part of the wave to the exact repeating part of the wave. So typically we represent it from the crest to crest, trough to trough, midline to midline, just the same point in the respective same place. So the time it takes to go across the wavelength is called 1 period. It's how long we have to go until we've essentially repeated this wave, as long as it's not deconstructed or interfered in some way, will continue on forever. And so the amount of time this takes is the period. And we also relate this to frequency. So the frequency is how fast this period is going per unit sequence. And so hertz is the base unit for frequency. We're primarily going to deal with wavelength. Lambda is this Greek letter, this weird one, and frequency f. Wavelength and frequency are inversely proportional because the speed of light is constant. So the speed of light is this horizontal direction. So it's just a linear distance traveled, not the total distance traveled across this wave. So as wavelength decreases, frequency increases to keep up with the speed of light. So visible light is probably the most important light to us because that's what we're able to see. That's what our eyes have evolved to register. It's what's probably most common in Earth due to our atmosphere and distance from the sun and all those type of things. So typically the longest wavelength associated with visible light is about 700 to 800 nanometers. That's red to infrared. Everyone's eyes are a little bit different. Different animals are different. Dogs see more in the infrared region than we do. They don't see vivid colors as well as we do, like blues and purples. So ultraviolet light is on the other end, and so that's usually considered somewhere around 450 to 350 nanometers, depending on what application you're looking at. A general range is from 800 to 400. The book gives 750 to 400, but I like 800 to 400. It's a little bit more round. And so we can take broad white light, like what comes from the sun, and we can put it through a prism and basically split out all the colors of light. The book gives you, red, orange, yellow, green, blue, indigo, violet. We typically just break it up into red, green, and blue, where red and green kind of both encompass orange and yellow. Orange is kind of a part of red, yellow is a part of a green. Blue kind of just encompasses all of indigo, violet, and ultraviolet. But you can break these down very particularly if you want. It's not much of an application in chemistry, but it might be for other fields. So in general, the reason we see colors is not because that color is being absorbed, but because that color is not being absorbed and is being reflected out. And we'll explain why certain colors are going to be absorbed in a couple slides, but in general, everything either absorbs or reflects light. If you see, something that's red, it's because it's absorbing all the other colors and reflecting the red wavelengths of light. If you see something that's white, it's actually reflecting all the visible spectrum, and so the entire visible spectrum, when we don't split it, is just a white light. And if we see something that's black, that means it's absorbing all the wavelengths of visible light. All right, so we talked about frequency a little bit in a previous slide. Sometimes you'll see frequency as V. The proper notation, if you're going to use V, is mu. Mu is a very hard, or sorry, nu, not mu, nu. Mu is for micrometer. Nu kind of looks like the letter V. But typically, when I give you equations with frequency, I'll just give it to you as F, lowercase f. But if you see nu or V, that can also be equal to frequency. So wavelength and frequency are inversely proportional. So as wavelength increases, frequency decreases. As wavelength decreases, frequency increases. So essentially what we're saying is, as this wavelength increases, so from very small to very large, the time it takes for it to go through one period also, or it increases. So over here, the time it takes for it to go through one period is much faster because the speed of light is constant. So the amount of the amount of horizontal distance it travels is going to be the same no matter the wavelength. However, the amount of distance the photon travels along this wave becomes more as the wavelength gets smaller. And so as it gets smaller, it's moving up faster and faster and faster. And so we can also say that its frequency is increasing, but its frequency is actually related to its energy. The faster something has to move, the higher its energy is. And we can relate this to temperature in some cases, but this is a different metric. And so the wavelength, the frequency of the wavelength actually relates to energy directly. So wavelength, increasing wavelength is inversely proportional to energy. So as we go to lower and lower wavelengths, our energy increases and our frequency increases. As we go to higher wavelengths, our frequency decreases and our energy decreases as well. So we have a whole bunch of different types of waves. You don't really need to be familiar with any types of waves. If you're going to memorize anything, memorize the visible spectrum. But we're just going to talk about a couple different types of waves, or rays is sometimes what we call them if they're very high energy. So gamma rays, they're not what Marvel will trick you into thinking. They are high energy waves, but they're basically produced from fusion of stars, things like that. There's not much gamma radiation on Earth unless you're doing some type of special radiological imaging for medical purposes. So X-rays we're probably a little bit more familiar with. These are a little bit lower energy than gamma rays. So X-rays are about on the wavelength of an electron. Gamma ray is significantly smaller than that by about 3+ orders of magnitude. So pretty small by comparison. X-rays will cause cancer and ionizing radiation in the body if you have a bunch of exposure to it, but it takes a lot of these by comparison to gamma rays and other things. So we obviously use these in X-rays and various other types of technology. So TSA uses X-ray for screening of luggage, things like that. Less energetic than X-rays would be ultraviolet rays. So this is what we experience in the sun. So the sun shines down on us. Our atmosphere doesn't perfectly filter out ultraviolet rays. Our atmosphere is really good at filtering out gamma rays and X-rays from, cosmological things, but the ultraviolet rays are pretty prone to getting in because essentially those higher energy wavelengths will energize the atmosphere, and then the energy from the energized particles in the atmosphere will then radiate other types of wave down that are less energetic in some cases. So ultraviolet waves will come through, they'll damage the DNA in your skin, and that's what causes sunburns. And so basically you have a sacrificial layer of skin that's giving up its DNA and killing itself off to protect the rest of your body. from having, you know, DNA replication errors that could cause cancers and other things. That's why overexposure to the sun will eventually cause cancer, but you don't instantaneously form cancer the first time you get a sunburn. So visible light is beneath ultraviolet light. So we've evolved to view visible light on a pretty wide spectrum. We're pretty sensitive to small changes in the electromagnetic spectrum. However, like I said, not all animals have the same visible light spectrum as us, so it's kind of relative to the biology of the organism. Infrared light is lower than what our visible light is. And so infrared light is essentially heat. We interpret infrared as heat energy. It excites, infrared light excites the water molecules, which are very present in our body. We're made of over 70% water. And so infrared molecules or infrared waves excite the molecules of water in our body and basically cause them to vibrate really fast and heat us up. We can use different things like infrared, night vision technology to kind of see in the dark because everything has some amount of temperature associated with it. And so you can get visions like, or views like this from infrared photography. The last type of electromagnetic wave we're going to talk about are microwaves and radio waves. These are much larger waves, so the wavelength of a microwave is about a micrometer. Radio waves are extremely large. They're typically much larger than, a human's height. And so these larger waves can travel much larger distances because their frequency isn't as fast and doesn't get deconstructed by other interference patterns as much. So microwaves are really useful for heating up anything with oxygen-hydrogen bonds. We've seen water. Water has oxygen-hydrogen bonds in here, and that's why it's such a good tool for heating up food. The reason why your glass always gets heated instead is because it also has oxygen hydrogen bonds in it that are a little bit more sensitive than most microwaves, but that's just an unfortunate side effect of the technology. So now we're going to talk a little bit more about photons. So photons are the particle version of light. Remember, we have this wave particle duality with photons as well as atoms and things like that. So the photon is basically the particle variant of this. We treat any given point on the wavelength as a photon if we were to draw it in. And so we can think of it as a packet of light. Sometimes it's referred to as a quanti of light, an individual unit of light. And the amount of energy carried depends on the wavelength of light. So we mentioned this. The shorter the wavelengths, the higher the energy. The greater the frequency, the higher the energy. So wavelength and energy are inversely proportional, just like wavelength and frequency are inversely proportional. Since wavelength is inversely proportional to both energy and frequency, energy and frequency are directly proportional. As one gets larger, the other gets larger. All right, so you can take a look at this slide. We've kind of covered most of this stuff. So as light waves carry more energy, their crest gets closer to closer, or their frequencies are higher, their wavelengths are shorter. Depending on what the wavelength is, shorter wavelengths carry more energy. Violet light is more energetic than red light. Kind of all the things we've been kind of going over. Likewise, if we have something that's ionizing radiation, the smaller the wavelength of that, the more damaging it's going to be. So just the generics that we've been covering the last couple slides. So we could do a quick approximation of these three waves of light: visible light, X-rays, and microwaves. So microwaves have the largest wavelength, visible light has the in-between wavelength, and X-rays have the smallest wavelength. So we could order them in terms of microwaves, visible light, and X-rays in terms of increasing frequency. We would flip that for wavelength. And frequency and energy are directly proportional. So visible light is, let me repeat that. Microwaves are less energetic than visible light. Visible light is less energetic than X-rays, and X-rays are the most energetic of them all. Frequency follows that same pattern. Wavelength is the inverse of that. All right, now we're going to talk about emission spectrums, and this is how we get very good color purity from electronics. And so what you see over here to the right is a neon sign display. Now this not be 100% neon in this sign, but the original signs that we did this type of lighting with were mainly composed of neon. And so we can basically flow specific amounts of energy through some type of atom or element, gas, chemical. As long as it's pure, we'll get really good color purity. And as long as we're only putting a specific amount of energy into it. So the element and the amount of energy depends. So over here we have a tube full of mercury vapors and a tube full of hydrogen vapors. If we flow the same amount of current through them, we get very different colors. And the reason for this is every element has its own identically unique emission spectra. So no two emission spectras are identically the same. And so you see that hydrogen has a pretty simple emission spectrum. Helium's a little bit more complicated. Neon is incredibly messy. And so we won't go into why these emission spectrums are different. It comes down to their electrons, the orbitals that their electrons are in. And neon has so many ultimately because it's a noble gas. And that's why the early neon signs were made of neon almost exclusively. Nowadays, they're made up of a whole bunch of things from neon, helium, hydrogen, krypton, various gases that are easily to source. So how we're able to figure out what the emission spectrums are is we use our slit and prism experiment again, and this separates the wavelengths this separates the broad spectrum light into the individual wavelengths, and then we could see what the actual spectrum is. So this comes about from the idea of these orbits. And so Niels Bohr was the first one to explain this, and he came up with this model, the Bohr model, where we have our densely positive packed nuclei that contains protons and neutrons, and we have electron clouds that surround the nucleus. And so what he said is these electron clouds orbit around the nuclei at specific radii. These specific radii are equal to quantum levels. We'll call these principal energy levels n. And so as we increase our energy levels, we get further and further away from the nuclei, and we get higher and higher energy electrons. These principal energy levels are synonymous with valence levels that we talked about before. Remember, every row of the periodic table is a different valence level. The first valence level is hydrogen and helium. Then the second valence level is that next level that has lithium, beryllium, boron, all the way through neon. Each one of these principal energy levels relates to the valence level. And basically what he theorized is that if electrons move between these levels, there has to be a change in energy. And so the thing that's not explained by the previous picture is that, or not explained as well, you can kind of tell, but the difference between these energy levels gets smaller and smaller and smaller. And at the very high, n equals infinity, essentially these energy levels blend together. At lower energy levels, they're, still differentiable, but once you get to very high energy levels, then they kind of just blend together, and we call them bands instead of orbitals. We're not going to talk about that. And so what Bohr was able to figure out was that if you add energy to a atom and it's able to absorb that energy, the energy is going to be directly absorbed by the electron, and it's going to be excited. However much energy is absorbed is exactly equal to the change in energy of that electron, or the excitation energy of that electron. Eventually, that electron will relax down to its principal energy level, or its ground state, where it originated from. If it was at, 0 degrees Kelvin, absolutely no energy, no excitation, where would that electron be found? It would be found in its ground state. After it's excited, eventually it will relax down to its ground state. Whatever energy difference is caused by relaxation is the same amount of energy that is released by the light, or the same amount of energy that is the light that is released. So when we have these neon signs or these tubes, this energy that is being emitted is directly linked to the energy that was absorbed. It is identical. So when we excite an electron, we will give off some sort of an emission. That emission will be exactly equal to the excitation and relaxation. Now, we don't have to do the same level of excitation as we do relaxation. So here you see that we're exciting from n equals 1 to n equals 3, and over here we're relaxing from n equals 4 to n equals 3. We're taking in some amount of energy, we're exciting some amount of energy, we're relaxing some amount of energy, we're giving off that same amount of energy. Now, we've said that the energy is directly proportional to the relaxation or excitation event, and so that's why, the n equals 4 to n equals 2 bigger transition is equal to blue light, whereas a smaller transition just from 3 to 2, so if I was going to go from 3 to 2, that would be an orange light transition, whereas if I was going to go from 4 to 2, a bigger relaxation event, I would get a smaller wavelength, which relates to higher energy. If I transition from lower energy orbitals, I'm going to get a lower energy relaxation or photon that's emitted. So we can look at this from the n equals 3 to n equals 2, we get red light. If we go just one more orbital or one more principal energy level, one more valence shell level up, we go from n equals 4 all the way to down to n equals 2. Well, then we're going to get blue-green light. Pretty high energy light, not really damaging to biological systems. But if we go up one more energy level, now we're into the violet range, maybe even considered ultraviolet for some people. This could damage your eyes. So as we get more and more energy levels that we're relaxing from, the larger the energy is going to be, or the smaller the wavelength it's going to be. Remember, wavelength is inversely proportional to energy, and frequency is directly proportional to energy. So the Bohr model is really good at explaining the hydrogen atom. Essentially, those fixed orbits are the average distance that electrons in those energy levels are away from the nuclei. That's why when I first introduced the Bohr model, I kind of said it's a really good approximation for the hydrogen atom. The quantum mechanical model actually solves the hydrogen atom. It doesn't approximate an average where the electrons are in any given energy level. It exactly proves and solves where the electrons are. And so because of that, our setup of the quantum mechanical model is going to be a little bit different. And so here's just some of the background on the quantum mechanical model. The big difference in naming is that we change our orbits in the Bohr model to orbitals. These orbitals are not fixed in their location or their distance, but they're probability maps, or what we usually call probability densities. And so you could think of the Bohr model as being a straight line. You always can predict where the ball is going. So if you're playing baseball, if you're the catcher, you can see where the ball is traveling. However, if you're looking at it from a statistics view, you could only see the probability of getting a strike or getting a ball, things like this. This is more what quantum mechanics does. It looks at the statistics of everything, and it maps the probability of any given event. And so we get probability density. So we'll have something called the s orbital that stands for the spherical orbital in just a second. And the s orbital is basically these spherical orbitals that get bigger and bigger depending on what principal energy level they are. And we can basically represent them as what is the probability that we're going to find an electron. And so as we make our maps bigger and bigger, we can increase the probability that we're going to find an electron in that space. And so we have these principal energy levels, just like we did with the Bohr model. These, again, just synonymous with valence level. We have principal energy levels, and then we have orbital type or orbital geometry. The first and simplest orbital geometry is going to be the s orbital or the spherical orbital. we're going to denote all our orbitals by letters. These letters relate to the fundamental mathematical shape that they take. However, the only fundamental mathematical shape that we're going to be familiar with is the sphere. So we're not even going to talk about what the p, d, and f orbitals mean. We're just going to show you their shapes. And so we talked about ground state versus excited state. The ground state is where the lowest energy state is. If you were to take something to absolute zero, give it no applied energy, no stimulus, that's where you would find the electrons. Now we can be much, much higher than absolute zero and still be in the ground state of a molecule. And it really depends on what type of molecule or what type of atom we're dealing with. The noble gases take an incredible amount of energy to excite them from their ground states, whereas something like fluorine wouldn't take as much energy, and you don't need to be too concerned with that right now. So as principal energy level increases, so too does energy. So we call it principal energy level because each level is synonymous with the amount of energy of those type of orbitals. So an n=1 orbital in the first row of the periodic table is going to be lower in energy than an n=2 orbital, or an orbital that's in the second row, third row, fourth row, fifth row, so forth and so on. So we have different types of shapes, or subshells, we refer to them as sometimes. And there are technically more than the S, P, D, and F, but they're more theoretical and they don't have any bearing on the chemistry that happens here on Earth or most places in the universe. So we're going to ignore everything that's not naturally occurring, essentially. So the s orbital is spherical, and we use these probability densities to kind of figure out where are we likely to find an electron. We don't know exactly where the electron is, and we can just show a general mapping of where an electron may or may not be at any given point in time with a certain level of confidence. And so what we'll show you typically is a space-filling model that would guarantee that 90% of the time you're going to find your electrons within that space. It's not 100% because we'd have to open up the volumes to kind of an unreasonable size, but to get 90%, 90% is good enough when we're talking about this type of things. So we'll have these little dots that kind of represent what the probability density is. And so you'll see that as you get further and further out, these are related to higher energy electrons. And so it's more likely that they're going to be dispersed near the center. And so those are going to be lower energy. And so the probability density increases as we approach the nuclei. And that kind of makes sense, is the nuclei is positively charged. It should attract the negatively charged surrounding particles. It's going to be harder to find something super far out from this densely charged nuclei than to find something closer in. The electric potential would be worse out here than it would be in here. So not all orbitals are the same. And so at the first energy level, if you look at your periodic table, you'll only see two elements. You'll see hydrogen, you'll see helium. Well, we only have one orbital for those two elements. We only have the s orbital. As we go to higher and higher principal energy levels, we're able to accept higher and higher levels of complex geometry. And what you should notice is that every principal energy level, we introduce a new orbital. So at the n=1, at the first valence level, we introduce the s orbital. At the n=2 level, we introduce the p orbital. These kind of look like dumbbells. At the n=3, we look at the d orbitals. And then at n=4, we're able to see the f orbitals. These get more and more complex in shape, and we'll go over the shape. But really, if you just remember the s and p orbital shape, that's all we care about right now, because the d orbitals are associated with the transition metals, which we already mentioned. We want to know about them, but we're going to kind of ignore them for the most part. The f orbitals are associated with the lanthanide actinides. Again, we're going to almost entirely ignore them other than just their existence. So we're mainly going to focus on s and p orbitals. So the s orbital is the perfectly spherical orbital. As we increase principal energy level, we increase energy. As we increase energy, we increase the average distance of the electron from the nuclei. And so the 1s orbital is smaller than the 2s orbital, which is smaller than the 3s orbital. The p orbitals are most commonly referred to as dumbbell-like orbitals because you could imagine there's a handle in here and these are two ends of a dumbbell. Pretty ugly dumbbells, but it kind of gets the idea across. We have three distinct p orbitals because we can have three mathematical arrangements of this shape that do not interact with each other. So we could have it along the x-axis, we could have it along the y-axis, we could do it along the z-axis. We could combine all three of these mathematical functions and have no coinciding terms. These are called orthogonal functions. We don't need to be comfortable with this, but if you go into more math, physics classes, or chemistry even, these type of terminologies will become more important once you're actually solving for, say the energy of an orbital or the energy of an electron. The d orbitals get more complex. I think we have a picture of them coming up here in a little bit, but again, we want to be more familiar with the s and p's. The d's are going to be less important if you go into an inorganic chemistry class or just more advanced chemistry classes. You're going to deal more with the d and maybe even f orbitals. We're not going to deal with them much here. And so they're pretty complex. So we basically have these, two dumbbells that are all combined into four orthogonal directions. So each one of these functions is completely independent of the other. And then you have this weird donut-shaped one that kind of fills in some of the spaces that are missed by all of these nodes. And so where these things kind of separate, we call these nodes. And that's going to be something that might be important to you later in your academic career. It's not going to be important for us in this class. So we went from orbits to orbitals. These orbitals are probability densities, and we can only put 2 electrons in them. In the Bohr model, we could put as many electrons as we had in each principal energy level. And so the first principal energy level, we have 2 elements, so we can put 2 electrons in. The second principal energy level, we have 8 elements, so we can put 8 electrons in. Same for the third. For the fourth valence shell, now we have 18 electrons. We have 18 elements that go across the fourth row. So we could put 18 electrons into the fourth orbit of the Bohr model. However, every orbital in the quantum mechanical model can only take 2 electrons. And so that's why we get more and more orbitals every time we increase the size of the periodic table. So when we just have the s orbitals in the first valence level, we can put 2 electrons in here. We only have 2 elements. Once we get to the p orbitals, the second row of the periodic table, we have 8 chemicals. So we need 8 electrons. Well, we can put 2 electrons in the 2s orbital, and then we can put 2 electrons in the px orbital. We can put 2 electrons in the py orbital, and we can put 2 more electrons in the pz orbital. So that would be 8 orbitals total. If you then consider the next 5 orbitals of the d orbitals, that's 10 more electrons that we can fit into the fourth row of the periodic table. Now what you'll notice is the 3d orbital relates to the fourth valence shell. And we'll explain that a little bit more in a second. And it's more just a mathematical procedure than something that we need to really get into the weeds about. So we have electron configurations and orbital diagrams. So we're going to start talking about these. This is where most of the problem solving is going to come for this chapter. Everything else is going to be conceptual. We're not going to, calculate wavelengths of light or anything weird like that. There are formulas for it. You can find them. It's pretty simple. It's very plug and chug type math once you have the equations. How we do electron configurations is we designate the principal energy level of the orbital, what orbital it is. Now we don't designate which subshell of the orbital is. We don't designate whether it's the px, the py, the pz, the dz squared, the dxy. We don't care about that specific nature. We just want to know how many electrons are in all of the given orbital of that type. So in hydrogen, we only have the first principal energy level. We only have s orbital for the first electron. Obviously, hydrogen is very simple. We'll get more complicated examples here in just a second. And so we'll move on from the electron configuration to the orbital diagram. So the orbital diagram is we show how the electrons are orientated or how the electrons are filling the orbitals of every given level. We typically will only do orbital diagrams for the valence shell, because only the valence electrons are really involved in any chemistry. Electron configurations will show the entire, however many electrons it has. If it's, atomic number 20, we'll show all 20 electrons and which orbitals they're in respectively. For orbital diagrams, we'll just show the valence shell. And so we have a couple rules for how we do these orbital diagrams. And so the first one is we have the Pauli exclusion principle. We've kind of already mentioned this, but orbitals can only contain 2 electrons. However, those electrons cannot be facing the same way. So we have this idea of electron spin. And it's not that these electrons are actually spinning in circles. That wouldn't make sense because you could, reorientate them and then they'd eventually be spinning the same direction. It's nothing to do that. It more has to do with magnetic properties of the electron, which is a bit more complicated than we're going to get in this class. So all we need to know is that electrons have spin. They can either be spin up or spin down. In order for us to put 2 electrons in a single orbital, we have to have opposite spins. So we cannot have paired spin. We can't have 2 spin up or 2 spin down. We have to have something that's 1 spin down, 1 spin up. And this is how we designate whether an electron is spin up or spin down. It's just by pointing an arrow up or pointing an arrow down. We typically use these half arrows because drawing a half arrow is just easier than drawing a full arrow. But you can use full arrows. It doesn't matter if you fill in spin up or spin down first. You just want to keep them consistent with how you fill them up. So those are the first 2 rules, is that we can only fill in 2 electrons into any given orbital. And that if once we put in our first electron, the second electron that goes in has to be the opposite spin. So I can put my first electron in as spin up or spin down, but whichever spin electron I put in first, I have to put the opposite spin electron in second. As we get to more complicated atoms with more and more orbitals, this gets a little bit more complicated. And so as we have different multiple orbitals within a subshell, like the p and d orbitals, because of these geometries, we have different energies between the s orbital and the p orbital and the d orbital. All of the 3 p orbitals and all of the 5 d orbitals have the same respective energy in the elements or the atoms. But the s to the p to the d are different. And so in here at the bottom, we see that the 4s subshell is actually lower in energy than the 3d subshell, even though 4s has a higher principal energy number. So these are part of the same valence shell, but they have different principal energy levels associated with the actual orbital. Remember, the p orbitals start at n equals 2, the d orbitals start at n equals 3, and the f orbitals start at n equals 4. However, the 6s orbital is the nearest energy orbital to the 4f orbital. So there's a lot of difference in that. And I'll give you some formulas and other ways to remember how and where which orbitals are placed in the energy landscape. So here's one diagram that you can use. This is just kind of memorization and doesn't even include the f orbitals. Again, we won't deal with things using the f orbitals often, if at all, but you should be aware of them. And if you're going to continue on in your chemistry career, you should be more and more ready to deal with f orbitals. So when we have two electrons, helium, it's pretty nice and simple. We just have the 1s orbital. We would say, He is the nomenclature for the chemical symbol. 1s2 is how we would say the electron configuration. And then we have a spin up and a spin down electron in the 1s orbital. If we want to go to the next chemical on the periodic table, lithium, not too much more complicated. We're just going to add an extra electron. We can't add more than 2 electrons to the s orbitals. And there's not more than one s orbital. There's only one sphere that you can, place in an individual area. So we only have one s orbital. So we need to go up to the next principal energy level and start at the lowest energy orbital. That's always going to be the s orbital. So we don't have any other orbitals until we get to the second principal energy level. That's when we introduce the p orbitals. The s orbitals are lower in energy than the p orbitals. So we'll fill up the s orbital. This will go pretty simple until we get to carbon and some of the other heavier elements in the p block. And so now we're going to introduce our second or third rule, depending on how you want to count them, is Hund's rule. What Hund found out as a physicist was that if we add electrons one at a time into orbitals, that it's more energetically favorable than anything else to add single electrons in parallel orbitals, or energetically equivalent orbitals, orbitals of the same subshell, so the px, the py, the pz, to fill them up singly with electrons of the same spin. What he found out was that if he put 2 electrons in the same orbital, opposite spins, that was higher in energy than putting 2 electrons with opposite spins into 2 separate orbitals, putting a spin up electron in the px and putting a spin down electron in the py. That was still lower in energy than putting them both into the px, but higher in energy than putting both spin up into the px orbital and the py orbital. So what we'll do as Hund's rule is we fill up equal energy orbitals with the same spin electrons until they're half full. Once we have a half full orbital shell, like 3 electrons in the 2p orbitals, which is what we would have for nitrogen, then we'll go and pair spin up and spin down electrons in the subsequent orbitals we started with. So here's a general ordering, if you like diagrams, that you can kind of draw. You can serpentine back, the particular energy levels. I don't like this diagram because I always screw it up when I draw it. The important thing to remember is at every new principal energy level, we're introducing a new orbital. So at the first principal energy level, we introduce the s orbital. At the second principal energy level, we still have the s orbital, but now we introduce the p orbital. Same thing with the third principal energy level. We still have the s and the p because we had them before, but now we have a new orbital, the d orbital. At the fourth energy level, we have a new orbital, the f orbital. Technically, at the fifth principal energy level, we have a new orbital, the g orbital. There's no naturally occurring elements that partake in the g orbital, so we don't even talk about it, but theoretically, you can put electrons into higher order orbitals than what exists naturally, but it requires a lot of energy. So when we write our orbital configurations and our electron configurations, again, I'm typically only going to ask you about orbital configurations of the valence level because they're very repetitive, but we want to start at the lowest energy orbitals, the s orbitals. We want to move to our higher energy orbitals, the p, d, and f orbitals. And we want to remember how the energy levels and the principal energy levels relate to each individual orbital. The 3D is lower in energy than the 4p, but higher in energy than the 4s orbital. We want to fill our electrons with opposite spins. However, if we're in a subshell like the p or the d or the f orbitals, we want to half fill our orbitals of the same type first with the same spin electron, so either spin up or spin down. And then after we've half filled a given orbital, so after we've put 3 spin up electrons into the p orbitals, then we can go back and start putting spin down electrons until we've fully filled our orbitals and have achieved that noble gas configuration. So here's just a couple examples of consecutive orbital diagrams and electron configurations. Again, Orbital diagrams are over here. Electron configurations are over here. In general, we like to offset our orbital diagrams depending on the energy landscape. So this 2s would be slightly picked up from the 1s. This 2p would be even slightly higher than either one of those. Usually we consider energy increasing on the, vertical axis, and number of electrons increasing on the horizontal axis. For sake of space, these are all, not considering the energy level. That's just a formalism for saving space. We go to the electron configurations. So we've been seeing that the electron configurations, we just count up. And so as we go to heavier and heavier elements, that's just a lot of, bookkeeping. There's just a lot of things that we have to run through till we get to the actual valence shell. The valence shell is where all the chemistry goes on. So why not just approximate everything in the previous, or the core electrons, as the previous noble gas configuration. So we have sodium. Instead of doing 1s2, 2s2, 2p6, we can just put brackets around neon, because everything in the third valence level, the third row of the periodic table, is going to have the core electrons that neon has in its octet. So why not just abbreviate it? And so if you don't remember that you can abbreviate these with the noble gas notation, that's totally fine. You can write out this whole thing. But that's a lot of opportunity to make silly mistakes and have me mark your answer wrong. When you could cut out a lot of the busy work by just bracketing the previous noble gas and then just showing the valence shell. So, valence electrons are the electrons in the outermost shell of the periodic table. So the book relates valence electrons to principal energy level, and this isn't identical. It's synonymous in most cases. For the main group, it is synonymous. Valence shell and principal energy level are the same. However, for the transition metals and the lanthanide actinides, the valence electrons are not always the highest principal energy level. As we saw, 3d electrons are part of the valence shell of the fourth row of the periodic table. So that's just a little oversight by the book. Not a big deal. So we have core electrons. This is everything that comes essentially in the noble gas configure, or the previous noble gas configuration. The valence electrons are anything that are going to be present in that bottom row of the periodic table where we're actually looking at. So silicon is in the third row of the periodic table. Its valence shell is going to contain anything in the third row of the periodic table. Remember, the 3D, the third principal energy level, starts at the fourth row of the periodic table for the d orbital. And so we don't include the d orbitals in here, even though they're in between the s and the p orbitals in the fourth valence shell. So valence electrons is where everything's going on in terms of chemistry. The core electrons are just kind of placeholders. They're just filling in space so that the valence shell can be on the outside. So here's just a whole bunch of electron configurations. You can notice that we're just slowly increasing. We're just adding one number until we fill up a given shell or given orbital of a valence level, and then we go to the next orbital of that valence level. And we just add one electron every time we move up. Pretty straightforward. So, we mentioned how there's a lot of periodic trends in the periodic table, and so because certain orbitals are going to have more or less electrons, they're going to be more similar or more near noble gases in different ways. Elements in the p block tend to be closer if they gain electrons to get to their nearest noble gas configuration, whereas S block chemicals will always lose electrons to get to their noble gas configuration. D block metals or transition metals tend to have varied behavior, tend to lose their electrons, but they can gain electrons. And the lanthanide actinides are very much the same as the transition metals, as they do whatever conditions allow them to when you expose them to different scenarios. So it's very common to talk about the S block, the P block, the D block. The S block is simply just the alkali metals and the alkaline earth metals. The P block is the part of the periodic table that's right of the transition metals. So most of the main group is the P block. The D block is the transition metals. The lanthanide actinides are the F block. So those ones are just straight synonymous with each other. We could look at this. This is kind of very similar to what we had on the what we will have on the exam. So instead of filling out D block and S block, you'll have halogens here. You'll have main group for here and these two. The S block elements will have to break up into the alkali metals, the alkaline earth metals, transition metals, lanthanide actinides. And then the noble gases, which is our ideal electron configuration, is right here on the end. Every time we get past the noble gas configuration, we go on to the next valence level. So in general, the main group elements have very predictable qualities. Everything in group 1 has the same behavior. Everything in group 2 has the same behavior. Everything in group, some people call it 3A. I'm going to call it 13 because you don't always get the A designations. The book's really good about it, but not everyone's going to do the same thing that your textbook does. It's pretty common to see 3A, which is the first group in the P block, as 13. So be comfortable with interchanging those. But everything in 13 has the same general properties. Everything in group 14 has the same general properties. 15 has the same general properties. 16, 17. Group 17 is the halogens. We've talked about how all the halogens take -1 charges when they make ionic compounds or when we ionize them. And so a lot of why they have similar properties is because their orbitals have the same occupancy. They need to gain or lose the same amount of electrons to get to the next noble gas configuration. This is true of transition metals as well, but it's a little bit more complicated. They have an 18 electron rule instead of an 8 electron rule. Anytime you have more stuff to deal with, it's just a little bit more complicated. So, transition metals have just the same electron configurations as main group elements. Their valence shell ends in the D block. Whatever block you're in, the S block, the D block, the P block, that's where your last valence electron is going to be. So if you're in the D block, whatever position I am in the D block, that's how many D electrons I'm going to have. Everything that comes before that, the 4s block and all of the core electrons, are going to be fully filled. So that means if I'm in the P block of the fourth row of the periodic table, I know that I'm going to have a completely full D orbital and a completely full S orbital. So, like last slide had mentioned, the transition metals have their own trends, albeit a little bit more complicated and confusing than the main group trends. And so one exception to the general filling of electrons is that for the groups of chromium and copper, so all of the elements in this row have this same trend, where they actually steal one of the electrons from the s orbital to completely half fill the 3d orbital. This is called Aufbau's principle, and it basically says that when we completely half fill an orbital, and so in this case the s orbital and the d orbital are completely half filled, they have all of their electrons unpaired, but fully filling the orbitals. Just one electron in each individual orbital. This has a special lowering of energy compared to unfilled or mix-filled orbitals. Again, I'm not going to ask you on the exceptions, but in later chemistry classes you might be asked about this exception. It's just because this half filling and full filling of the d orbital provides an extra stability that we don't get from having a mixed or partially full d orbital and a fully filled s orbital. Copper, we have a fully filled d orbital and a partially filled s orbital instead of 4s2 3d9, which would be a fully filled s orbital, which has some special stability to it. But then we'd have a 3d9, which has no special stability. 3d10 is fully filled, which has special stability. 4s1 is half filled, so it has special stability. Both of those halves, or both of those special stabilities, is better than just one of them having special stability. In this case, same idea. Better to have both of them having exceptional stability because of the half filled than to have one of them completely filled and one of them being mixed. Weird exception, but it comes down to the wave equations and the mathematics. So, in general, like I had mentioned a couple slides ago, whatever block your element is in, that's where your last valence electron is going to be present. So if we were to look at phosphorus and give the electron configuration for phosphorus, we'd find phosphorus. Okay, P is phosphorus. Okay, that's in the P block, so it's definitely going to be the periodic table, or the P orbitals. Sorry, it's definitely in the periodic table. It's going to be in the third row, so it has to be the 3P. Okay, it's 1, 2. It's in the third position of the P block, so it's 3p3. And then it's going to have everything before that. So it's going to have all of the 3s filled. It's going to have all of the inner core electrons from neon, but that's just 2p6, 2s2, and 1s2. Obviously, we'd write that in the reverse order because we want to start with our lowest energy orbitals first. So inner electrons come first, or we can just notate it with the noble gas configuration. So I take the previous noble gas, put that in brackets, and then I start working on the lowest energy orbitals. I'll go over a mathematical formula for it that you can tell which orbital comes in the problem solving session. But for now, the S is the lowest in energy, P is the second lowest, D is the next lowest, F is the last one that we'll ever really deal with. However, the 3D sits in between the 4S and the 4P. And at the 6th principal energy level, the 6S is the lowest. Then we go the 4F, the 5D, and then back up to the 6P. So it's a little zigging and zagging. We showed that diagram that kind of approximated it. So highest principal energy level is going to be basically the row of the periodic table. We want to focus more on valence shell rather than principal energy level when we're talking about this because, like we've mentioned with the D and F orbitals, those can be the outermost electrons in the given valence shell, but they don't have necessarily the highest quantum principal or the highest principal quantum number. So why we use these models is because they allow us to make predictions and ultimately create technology with pretty high precision. And so what we do is for the main group, we have this 8 electron rule or octet rule. And so elements that have 8 electrons tend to be the noble gases. And so every other element within the main group is going to gain or lose electrons to try to reach that octet, because fully filled orbitals have a special stability that half-filled and mixed orbitals don't have. Again, 2 half-filled orbitals is better than 1 filled orbital and another mixed orbital, but in general, the best thing to do is have completely filled shells of orbitals. So we want to completely have a valence shell full. So, the valence shell of the first row of the periodic table is just the 1s orbital. The valence shell of the fourth row of the periodic table is the 4s orbital, the 3d orbital, and the 4p orbital. Typically, we won't talk about the d orbitals. They do pertain to the main group in certain cases as we deal with heavier and heavier elements, but it just gets a little too complicated for an intro class. So, we had mentioned that alkali metals always form +1 charges. This is because they can give up 1 electron and take the previous noble gas configuration. Halogens, on the other end, will always gain 1 electron to get that noble gas configuration to fully fill their p orbitals. They're missing 1 unpaired electron in their p orbitals, so they'll snag 1 electron, fill up that p orbital, and have a full octet, or that noble gas configuration. essentially whatever group, 2A, anywhere in the main group, you can predict what type of cation or anion is going to be formed based on how it gains or loses electrons. Now, some of these elements, they always do something. Groups 1 and 2, the S block, the alkali metals and the alkaline earth metals, they're going to always make positive charges. There's, 1 in a million examples where alkali earth metals make an anion. And it's usually when they're binding with other alkali earth metals. However, in the main group, we have a lot more mixed, or sorry, not the main group, these are both the main group. In the P block, we have a little bit more mixed charges that can happen. So the book's a little misleading. The halogens, it's pretty true that 99% of the time they're always -1 charge. The exceptions are when they're bound to other halogens or if they're bound to oxygen. However, sulfur, selenium, and beryllium, they often make positive charges. We're going to see a lot of examples where nitrogen forms positive cations and things of that nature. And so I would say everything other than oxygen and the halogens has a mixed charge. The way we know what that charge is going to be is dependent on what the most electronegative atom is. Remember, the most electronegativity is a periodic trend that starts in the bottom left corner, where francium is, the element below cesium, and increases as we go to the top right corner, ending with fluorine. We ignore the noble gases. They don't want to gain electrons, so they don't have an affinity for electron. Electronegativity is this measurement of how hard an atom pulls on other electrons. So the fluorine nuclei pulls on electrons harder than any other nuclei on the periodic table. The amount of force that it wants to pull on another electron to get to its next noble gas configuration is stronger than any other element. The next strongest element is oxygen, followed by chlorine, and then so forth and so on as we zigzag across the periodic table. But in general, this increases as we go up the periodic table and to the right. I'm never going to make you split hairs about going diagonal to the left. If you remember that oxygen is more electronegative than chlorine, that's great. But this diagonal to the right, it's not always guaranteed that the top left one is more electronegative than the bottom right one. However, it's always guaranteed that if I move up the periodic table, I'm increasing in electronegativity. And if I move to the right on the periodic table, I'm increasing in electronegativity. Fluorine is the most electronegative, then oxygen. That's about as far as you need to get. So fluorine and oxygen will always be negative charges, no matter what. Chlorine, bromine, and iodine will almost always be -1 charges, but there are more examples than, fluorine and oxygen where they don't have a negative charge and they actually take a positive charge. If I have to move 1 to the right to get my negative charge or my octet, I'd have to move 7 to the left or gain a +7 charge to reach the previous noble gas configuration. Since that's so many electrons to give up, it's very rare that we see that. However, it's pretty common with sulfur and especially phosphorus. Nitrogen, we move 3 positions to the right to get to the noble gas. We have to move 5 positions to the left to get to the previous noble gas. So group 2, or sorry, not group 2. Group 1 and 2 will always be +1 or +2. Group 3/group 13 will always be plus or -3. This is because group 3 will essentially just ignore its s orbital and only use its p orbitals. Kind of that exception we saw with copper and chromium in the D block. Group 3 or group 13 is the same exception in the main group, is they just kind of ignore the s orbital, they unoccupy the s orbital, and fully fill their p orbital, or fully empty their p orbitals, or all of their orbitals, really. And so they take ±3 charges. I won't really talk to you about these much. They're very important in organic chemistry and catalysis. Group 4 is going to be ±4. It's right in the middle of the octet, so if it's bonding with something that's more electronegative than it, nitrogen, oxygen, fluorine, it's going to form a +4 charge. But if it bonds with something that's to the left of it or down of it, it's going to take the -4 charge. So if carbon bonds with hydrogen or lithium or sodium, carbon's going to be the negative charge, and whatever it's bonded to the left of it will be the positive charge. So if nitrogen or if carbon was bonded to boron, boron would be a -3 charge. Or sorry, boron would take the +3 charge because it's less electronegative, and carbon would take the -4 charge because it's more electronegative. Now you'd need multiples of each to balance out the charge perfectly. You'd need 4 borons to every 3 carbons, but that's not important here. We'll talk about that in later chapters. So, in general, we can know what types of charges are going to be likely to be taken by any element based on its periodic table. The only ones we can guarantee as 100% are the S block elements, as always being, alkali metals are always +1, alkali earth metals are always +2, the halogens are always going to be -1, and then oxygen's always going to be -2. Based on those absolute given rules, and remembering that things that are more electronegative are going to take a more negative charge than things that are less electronegative or more electropositive. They're opposites. Electronegativity is the pull for an electron. Electropositivity is the pull for a nuclei. Opposite ends of the coin. So the next periodic trend we're going to talk about, and it's pretty common, is atomic size. This can also be related to electronegativity. Essentially, all periodic trends can be related to electronegativity, and that's how I like to think of them. It's not required. You can just memorize every given periodic trend. But in general, atomic size is the distance of the electron cloud to the nuclei. The most important thing for atomic radii or atomic size, radii is just the distance from the center to the outermost edge, whereas the diameter is from one outer edge through the center to the other outer edge. Mathematically, we typically use radii instead of diameter. But the most important thing to determine the size of an atom is its principal or its valence shell, so its highest quantum number. So, if it's n equals 4, it's going to be larger than n equals 3. So sodium is larger than hydrogen because it's just lower on the periodic table by 1 valence shell. In general, as we go across the periodic table to the right, as electronegativity increases, the pull on those electrons is greater. So if the pull on the electrons is greater, those electrons are going to be, on average, a little bit closer to the nuclei. And if on average any given electron is a little bit closer to the nuclei, the average size of that nuclei is going to be smaller. So fluorine is smaller than oxygen, which is smaller than nitrogen. But if I go down the periodic table, I'm just going to increase size no matter what. So atomic size is inversely proportional to electronegativity. So as I become less and less electronegative, atomic size tends to increase. But more important than electronegativity is principal quantum number, or valence shell. So as you move down and to the left, size increases. So kind of the opposite of electronegativity. As you move to the right and up, electronegativity increases. Well, atomic size is inverted to that. And so here would be a nice little slide that, in the top right corner, we're the smallest. And as we go down to the bottom left corner, we get larger and larger and larger. This is only for neutral atoms. If we have ions, this is a little bit different. So ions tend to actually have the opposite behavior because things towards the left of the periodic table form positive cations, so they give up their outermost shell of electrons. So cesium ion will actually be smaller than a astenine ion because astenine is going to have a full 6th valence shell, whereas cesium is going to give up its 1 electron in the 6th valence shell, and it's essentially going to have the same atomic size as something in the 5th valence shell. it's going to be a little bit more electropositive than something in the fifth valence shell, and so its valence electrons will be pushed out a little bit more, but not as much as if those electrons were actually in the next valence shell. Ionization energy is another trend. So ionization energy is the energy required to remove an electron from the atom in the gaseous state. We also have what's called ion affinity. This is basically the energy required to add an ion or add an electron to something. So they're opposite ends of the coin, depending on what your field does, whether you're an organic chemist versus an inorganic chemist. Depending on what type of science you look at, you might be more concerned with ionization energy versus ion affinity. My grad school work, we did a lot of ion affinity, so I thought of it more as the energy to accept an electron rather than this is the energy required to remove an electron. So ionization energy increases opposite to electronegativity. So electronegativity is the pull on electrons. If the pull on electrons is, increases as you go up into the right of the periodic table, it's going to be harder and harder to ionize those electrons, to remove an electron. If it's trying to pull electrons to it, it's going to be harder to take electrons away from it. So fluorine's going to have one of the highest ionization energies. Now, the thing with ionization energies and ionization affinities is the noble gases are exceptionally resistant to change. They don't want to gain or lose. So noble gases have extremely high ionization energies and extremely high ion affinities. Whereas most other chemicals, as their ionization energy increases, their ion affinity decreases. Ionization energy is the energy required to remove an electron, and so that energy is going to increase as we go up and across, or across to the right of the periodic table. So up and to the right. Same general trend as electronegativity. So ionization energy decreases as we go lower and lower, and increases as we go to the right. So it's harder to pull an electron from something that's right nearest to its noble gas than it is something that's just dying to give up an electron. So sodium has extremely low ionization energy because all it wants to do is get to the nearest noble gas configuration, which is just one electron away. All it has to do is pop off one electron and then it's perfectly stable. Whereas chlorine, it has to pop off 7 whole electrons until it can get to a stable configuration. That's going to be really hard. Every time it pops off an electron, though, that ionization energy is going to go down slightly because it's closer and closer and closer to the noble gas configuration. However, every time you remove an electron, you need more and more energy, so you need a ton of energy to remove 6 or 7 electrons from chlorine to get to the neon configuration. So again, ion affinity or ionization energy, which is the opposite of ion affinity, is going to have the same trend as electronegativity. The book displays it as decreasing down and increasing to the right, but we could say it's increasing up and increasing to the right. I like to think of things with similar comparisons. I don't like to say decreasing with respect to this while increasing with respect to this. I might as well just say increasing with respect to this and increasing with respect to that. That's personally how I like to see it. The book obviously orchestrates it a little bit differently, so I like to explain it in both manners. So, we talked a whole bunch about light, waves, how they behave like particles, and they have that wave-particle duality. We mainly want to be concerned with how energy and wavelength and frequency all relate to each other. So energy and frequency are directly proportional. Energy and wavelength are inversely proportional. And wavelength and frequency are inversely proportional. So we can interconvert all these things. We talked about a whole bunch of different types of waves of light, from ionizing radiation to very low energy wavelengths like radio waves. You don't need to memorize anything particular about any type of wavelength of light. Just be comfortable with them. We talked about the Bohr model. You definitely want to be comfortable with the Bohr model, and especially with how it explains excitation and relaxation in terms of atomic emission spectrums. We have the quantum mechanical model that specifies orbitals. And so we really want to be comfortable with orbitals and how we represent them, how we talk about electrons filling different orbitals, energy levels of these orbitals. We have electron configurations and orbital diagrams. That's going to be most of the problem solving for this chapter. Everything else is going to be very conceptual. We had the periodic table. We looked at it and broke it up a little bit more than just, the names of the groups. We broke them up into the orbital blocks. We can generalize a lot of their properties, not only by their group numbers, whether it's the alkali metals, the alkaline earth metals, but also based off of their orbital block. S block elements tend always almost lose electrons to become cations. P block elements tend to gain electrons, but they have a little bit more mixed properties. But in a given row, they tend to behave very similarly, so forth and so on for the D block and F block. We want to remember our periodic trends. Again, I would try to relate all of my periodic trends to electronegativity. Electronegativity is the overarching thing. Remember, I say that chemistry is always the study of how electrons interact between different atoms or different molecules. And so if you study what makes electrons move, electronegativity, you can be very good at assuming what molecules and atoms are going to do. So size is inversely proportional to electronegativity. So as we go to the bottom left of the periodic table, size increases. And then we also had ion affinity or ionization energy. Ionization energy is synonymous with electronegativity. It increases as we go up and to the right. Ion affinity, which is the opposite, the energy required to put an electron into something, is a little bit opposite of that. So, atomic theory, we talked about that. Periodic trends, electronegativity most importantly. The orbitals, S and P orbitals. You only really need to be concerned with the S and P orbitals. If you know the D orbitals, awesome. If you know the F orbitals, even better. You do need to know how they're energetically arranged. So you should know that the 4s orbital comes before the 3d orbital, but the 4p orbital comes after both of them. You need to know that so that you can do your electron configurations and your orbital configurations or orbital diagrams.